How's everyone doing? My name's Dr. AJ Kumar, PhD. The last video, my OBS crashed, but it crashed right at the point, right at a natural stopping point in the video, right actually at the stopping point that I had anticipated, so actually it worked out. So anyway, this we're talking about what sounds like a lot of jargon, but I promise this will make sense. Affine construction of signed measures, and this is Abstract Algebra 10. So recall from Abstract Algebra 7 this pattern that if you have a vector u and a vector v, then the determinant of uv, what I mean is if you pretend u is a column vector and v is a column vector, and you make the matrix of the two of the column vectors next to each other. So this is a determinant of a square matrix. This is the signed area of this parallelogram, and if you swap the two columns, you get the minus signed area. And this corresponds to the positive signed area corresponds to a counterclockwise orientation, and negative signed area corresponds to a clockwise orientation. So the typical way you think about this is you use something called the right hand rule. And so what you do is you take your right hand and you curl your fingers in the direction of the rotation. And then if your thumb points out of the monitor, so if your thumb points out of the monitor, it's positive. And if your thumb points into the monitor, it's negative. So counterclockwise rotation, take your right hand and curl your fingers in the direction of the rotation. Your thumb will point out of the monitor. If it's counterclockwise, that's positive orientation. And the right-hand rule is going to become more important than this sort of polygon picture later on. This is sort of hinting at a larger subject that's called geometric algebra, which is really important. So anyway, the standard picture, the counterclockwise orientation is positive. So if you have a counterclockwise oriented parallelogram, it will have positive orientation, and clockwise orientation is negative. And I want to point out, so this is what I was talking about earlier with the truth versus reality thing. This depends on the convention for how we draw axes. So this depends on the x being the horizontal and y being the vertical axis. Well, if that convention was reversed, then so would the clockwise counterclockwise thing. So what I mean is the algebra or the math is independent of the pictures. And so I have a phrase, God doesn't care about geometry. And this is what I mean. There's this saying, the deepest truths of the universe are written in differential geometry. That's precisely the opposite of my experience in math. My experience in math is that the deepest truths have nothing to do with geometry, and that the geometry is really hinting at something that's more fundamental. So in this case, I have the x-axis being the vertical axis and the y-axis being the horizontal axis. And in this case, I've just drawn the same picture as up here, but with the x, y reflected along the line y equals x. So in this case, we have something interesting, which is, well, the blue orientation, which was clockwise up here, or counterclockwise up here, has become clockwise down here. And the yellow orientation, which was clockwise up here, has become counterclockwise down here. But we still have the case that with the blue orientation, is positive and the yellow orientation is negative. That's true in both pictures. But now in this bottom picture, the yellow orientation is counterclockwise and the blue orientation is clockwise. So my point is the counterclockwise clockwise thing, that's an artifact of the way we choose to draw pictures and is not intrinsic to the mathematics. Mathematics doesn't really necessarily have a notion of counterclockwise. It does have a way of establishing a uniform sign convention for orientations, which is precisely this, but it doesn't know what clockwise versus counterclockwise means. That's a product, that's an artifact of how you draw a picture. All right, the general picture. So this is a very big picture that we're going over right now. The general picture in which linear algebra operates is something called affine geometry. And I want to mention that this is distinct from Euclidean geometry, which is not what we're doing. And I'm going to go over why that's a different thing. Okay, so the rules, this is a rough presentation. Again, I'm just trying to explain what's going on, not trying to give a full singing, dancing, rigorous analysis. Just trying to explain what's going on. Rough presentation. Okay, we can draw straight lines. We have a notion of parallel lines. So given a line L and a point P, we can construct the unique line M that is incident with P and parallel to L. So here's a picture, here's L, here's P, and here's M, which is parallel to P. If P happens to lie on L, then M is equal to P. Okay? We can form the meet of two lines that are not parallel. This is important. So I denote this with an S expression, M, L1, L2. Okay? And we can form the join of two distinct points, which is a line that contains the unique line that is incident with both points. At P1 and P2, so up here, two lines that are not parallel will meet in exactly one point. We've mentioned that before. And the join of two distinct points, you can't join, there's an infinite number of lines that go through a single point, but if you have a point and another point, there's only one line that goes through both of them, and that's called the join of the 2 points, which I denote simply as J, P1, P2 in an S expression. All right. Now, in a preview of the future, so in a few videos, we're going to zoom out and look at a more general picture called projective geometry. And this is a little bit more powerful because we don't have to, tiptoe around these special cases. For instance, the meet of two parallel lines is well defined. There's a line at infinity in projective geometry, and I promise it'll make sense. There's a line at infinity in projective geometry, and the meet of the two parallel lines, well, they meet at a point on the line at infinity. And then, it fits naturally into the algebraic story. So stay tuned. That's coming. So what I want to conclude with is a demonstration. So our rules are, can draw straight lines, you can form a parallel line, you can form the meet of two lines, and you can form a join. We can now do two things. We can do three things, actually. Number one is construct a grid plane, and I made this slightly off of perpendicular to emphasize that this does not have the Euclidean notion of right angles. We can actually measure angles in a really interesting way, and I'm going to talk about that in another video. We can come up with a perfectly consistent way to measure angles. And we can also, you can measure quadrants, and in the rational framework, and in the irrational framework you can also measure distance, because you take the square root of quadrants. And if you you'll hear geometers talking about a system of rulers and protractors. That's what they mean, is that there's a local affine geometry. And I want to mention that this is different from Euclidean geometry, which has this additional tool called a compass. Not like a north-south compass, but it's like this little tool where you stick a pin. Look up what a compass is on Google Images if you don't know. But you put a pin down here, and then you... where's my pen? Okay. Here, let me just try to draw what it looks like. So it looks like this. So, okay. So there's like a little pencil end over here, something with like ink, and then there's a pin down on this end, and then there's a hinge up here which you can, or with a screw, which so you can tighten it and make the length constant. And then from that, you can draw circles. And so, well, if you can draw circles, then, for instance, you can also do things like, well, you take a circle, you take 2 points, you form the line that joins the two of them, right? And then you take a circle, so let's call the left point A and the right point B. You take the circle at A, circle centered at A that goes through B, and the circle centered at B that goes through A, and you make them the same radius. Then you can form these joins up here with these 2 points of the 2 circles. You find find the 2 meets of the 2 circles, and then take the join of those 2, and then you have a line that is what's it called, a perpendicular bisector of this little line segment. So this introduces the Euclidean thing, introduces irrationalities, so that's not what we're doing. We're sticking within a perfectly rational framework for the time being. Okay. So I want to show you how, just with these rules over here, I can construct a grid plane. And again, we have a perfectly consistent notion of angle, but whether or not it matches the normal notion of angle is a byproduct of how you draw it in space. So this is what I mean. The truth is different from reality. Okay, we can construct a perfectly coherent truth story that may or may not match reality. So how do we do this? So what we do is so I'm just going to pick any point over here. Doesn't matter where. And let me make it really big. Okay. Now what I can do is draw the blue line that is or a line through this point that is parallel to the blue line. So let me do that. Let me zoom in. Okay, and then let me make this bigger point. Ooh, that's too big. There, that's perfect. All right, and then I wanted it to be closer to being through the center, but well, we'll live. Okay, and then can draw a line that's parallel to the pink line. Okay. And the thing is, if you screw this up even a little bit, then you notice it a lot. So, nope. Nope. That's good enough. Okay. Okay, now what I'm going to do is take the join of these corners. So let's make this yellow. Actually, let's make it white. Make it really small. Right, we can take joins we can take as many joins as we want, and then we have these 2 lines. We can form their meet, which is this point in the middle, but I'm not going to draw it because it clearly exists. And then what we can also do is construct a parallel line. So let me do that. So I'm going to oops. Y. Okay. And let me make this. Should I make it blue? Maybe let me make it dark blue. Okay. I can't see that. Yeah, okay, you got to be really, really careful with this. Okay, here we go. Okay, now what I can do is take this, let's go back to white, and join this line with this, join the origin, that intersection of the big blue line and the big pink line is what I'm calling the origin, and take the join of the origin with this point that I've constructed over here, and just keep extending that until I hit the blue line again. Okay. Now what I'm going to do is call, maybe make it really small. I'm calling this point, this is the point 1, 1. That's what I was doing initially. And this is the point 1/2, 1/2, and this is the origin. Okay, well this line now has a slope of 1/2, so this point over here will now be the point 2, 1. Okay? And let me just show you. Okay, let me just try to, too big. Why does it keep switching the marker on me? Is there like some keyboard shortcut I'm hitting or something? Okay, you see now that, well, now I can construct 2, and then using a similar procedure I could construct the third one, and I can also go the other direction. And I can also construct more, I can also construct horizontal lines, so I can construct more blue lines. So maybe a way to do that would be, well, let me pick a darker purple. So to construct more blue lines, what I would do is go here. What is going on? What is going on? Why is it? This program has been messing with me all day. Okay, and then I can take white and go from here to here. Okay, and now I can construct more blue lines, because I can construct parallel lines. And I'm going to be sloppy just so that I can go faster. Okay, and I'm going to construct one more blue line. How should I do that? Yeah, so what I can do, I can go from down here up through here. That looks good. Get another blue line. This is so frustrating. Imagine how long it took me. This is so frustrating. This is a good exercise for you to do at home, by the way. And I'm just trying to show you what's going on. Okay, and then let's go up here. Okay. What I can do, actually, you know what I want to do? I want to construct one below. So how do I get a point down here? So what I'm going to do, I'm going to there we go. That does not look parallel. Did I make a mistake? Nope. Appears that it's just an optical illusion that these two are parallel. Or maybe the program has some bug in it. Anyway, so let's see, how do I get a point down here? Here's what I'm going to do. I'm going to join this up here. That can't be right. That's what I'm going to do. There we go. There we go. There we go. Now this down here is the point, this point over here. If I am not recording, I'm gonna do something horrible. I am recording, thank God. Let me just save this. Okay. Starting down here, what I can do is I can go, well, if I go over, let's say I go over 2 and up 3. So over 2, 1, 2, 3. And let me pick a new color. I'm going to pick green. There's a lot of lines here, but hopefully. And I'm going to join down here. And I'm also going to go, what's a color I haven't used? I'm going to use orange. Over 1 and up 3. And what I'm going to do is make a circle. Make circles. So just so that you can see. Okay. Uh-oh. There we go. The point is now I can construct any fractional point. I've constructed the point 1/3 and 2/3 here. And just using the same procedure, within finite time, I can construct any fraction. Okay? And I can also do the same thing on the sort of kind of vertical axis, the pink axis. I can construct fractional points, and then by making parallel lines, I can construct any point with fractional coordinates. That's what I wanted to show. So I can construct the grid plane, and I can construct rational coordinates, so coordinates that are fractions. All right. Next video, because I'm really frustrated, we're going to compute, and I was pretty intelligent about figuring out when I would need a break. All right. Compute signed areas of oriented polygons with rational vertices. So what does that mean? I'm just going to give you a little preview. What it means is that you can draw any polygon in the plane as long as it has rational vertices, and you have to pick an orientation to it, and we can compute its area. And that also, it generalizes to higher dimensions, and we can talk about volumes in 3 dimensions. We can talk about something a little bit more abstract than volumes in 4 dimensions, and the general idea of volume is called measure. So that's why this video is, where is the title? Affine Construction of Signed Measures, Part 1. Okay, I guess that'll be the part where we actually construct the signed measures. I wanted to show what affine means, and these are just the tools we have. Again, the tools: drawing straight lines, drawing parallel lines, forming meets and joins. And that's all we need to do, and we can construct the affine plane, and given the affine plane, given 2 specified directions, and you just pick an arbitrary unit for this is equal to 1. Given the affine plane, from that we can also construct a perfectly consistent notion of area, and we can also construct a perfectly consistent notions of can't do angle, length and so if you're willing to do irrational geometry, you can do length and angle, and I think in our geometry we can do quadrance and spread, which would be Wildberger's rational trigonometry. Go look that up if you want. I'm done. All right. Thank you for watching.